Okay friends, let's do some more probability distributions. We're going to keep it theoretical in this video. We're going to use coin flips. We're going to flip a coin a certain number of times. And even though I just got done saying that theoretical distributions are less useful, and they are, I mean, like I said, coins, dice, and cards, I like to add to that a few others, but they're all based on gambling, like the roulette wheel or a one-armed bandit in a casino, or even like a Powerball ticket. All of those things you can know the theoretical probabilities of as well. But the only reason you could know them is, well, there's twofold. Number one, and we'll study this later in day 3 of this lesson. Number one is every one of those games is slanted against you, and we'll see how later on. And number two, you can actually observe or keep track of all of the results. Even something massive like a Powerball ticket. There are hundreds of millions of possible Powerball tickets, but you know that there are hundreds of millions of them. When it comes to studying, say, human behavior, for example, it's much, much harder to delineate every single behavior someone could do. So you have to watch a number of them and gather those results. That does get daunting. We'll come back to it. It's mostly in Math 244, honestly. We'll come back to it in 243. But while we're getting this idea about distributions down, I think it's probably easier just to talk about more theoretical stuff that we already know. So let's do coins in this video. So for this next experiment, let's talk about flipping a coin one time. Okay, that's going to be our next experiment. Flip a coin one time. What can happen? Now, what makes this a little bit interesting is we called the X column, the left column of the T-table, the result last time. And mathematically, you want that column to have numbers in it. So what you don't want to write is heads and tails, even though that's actually what could happen, heads or tails. But because we're going to manipulate these distributions numerically, you want to have numerical data in there, not qualitative data. You don't want to say heads and tails. So I think an easy way to get around this is to say X equals, how about the number of heads? Number of heads. And then if you flip a coin one time, you either get no heads, which means you got tails, or you get one head, which means you got heads. Now, what are the probabilities of those numbers? So I'm using the X here, again, because it's a random variable. What's the probability that the random variable equals each of these numbers? Don't overthink it. You already know this. It's 50-50. It's 1/2. It's 0.5. That's what the entire distribution will look like. Pretty straightforward. If you flip a coin one time, you're either going to get no heads, which means you got tails, or you're going to get one heads. Piece of cake. That's your distribution. We're not going to do anything with it. I don't want to do anything with it. I'm just trying to get you to see as many different of these T-table kind of setups as we can. Let's clear the board and flip a coin twice. Okay, now we're going to flip a coin 2 times. So how many heads could we get if we flip a coin 2 times? Well, we might not get any. We might get tails both times, right? That's true. We might get one of each, or we might get both heads. So I think those are all the possible values. And this is where I really miss being in class with you all, because I love asking you what chances should go in that column. You know, what chances should go in that column. So because you're not with me, I'm going to kind of pretend that you are. And what I usually have my students do when we're in class together is write out all the possibilities of what could happen. Now, depending on if you had me for Math 105 or if you've had some probability statistics kind of classes before, you might realize right away that there are 4 different things that can happen if you flip a coin 2 times. And we did mention this in the very beginning of the course. We were talking about this idea of repeated multiplications. We'll come back to it too in here. And the reason it's 4 is because each coin flip has 2 results. 2 times 2 gives you 4. We're getting a little ahead of ourselves here, but I think you can handle it. And the results would be heads and heads. That's one result that can happen. You might flip heads followed by tails. You might also flip tails followed by heads. That is those are 2 different results. And if you don't believe me, and I always encourage my students not to believe me, imagine having 2 coins, you know. one of which is heads, and one that's a lot of focus. This one's heads and this one's tails. Well, that's a different result than if I was to flip them both the other way. Those are two different results. It's both one head, one tail, but there's two different ways it can happen. And then the last way is two tails. So, 4 outcomes. Hopefully it makes sense now. One of the 4 is both heads, and one of the 4 is both tails. That means that each of these n probabilities is a quarter. So it happens 25% of the time. The other 2 out of 4, or 1/2, has to be the 1 and 1 case. And you can always check your distribution by making sure that the probabilities sum up. That's terrible. I'm going to write this facing the correct way. The sum, there's our good buddy big sigma. The sum of the probabilities are always going to be equal to 1 if you've set up your distribution correctly. So you're twice as likely to get one of each as you are to get either both heads or both tails. Or said a different way, I mean, you can also say it a different way, you're just as likely to get one of each as you are to get them both the same. Cool. Let's flip 3 coins next. Okay, next experiment. Flip 3 coins. Now, I also want to say, I chose to keep X is the number of heads. You could have just as easily called it the number of tails. This is called a binomial distribution, because only 2 things can happen, heads and tails. And it's a symmetric binomial distribution, because the chance of either heads or tails is the same, 0.5. We'll delve into that a lot more in the next topic, which is called the binomial distribution. So if you flip a coin 3 times, how many heads could you get? Well, you might not get any. Hopefully you're seeing a pattern here. You might get 1, you might get 2, or you might get 3. Now what I want you to do right now is try to fill these probabilities in. Try to fill those probabilities in. Hit pause on this and give it a shot, and then come back. All right. Maybe you played along, maybe you didn't, I don't know. This is, again, I wish I was in class with you. You could actually list these out just like we listed out the previous ones. Since each coin can happen one of 2 ways, you're going to have 8 total results. 2 times 2 times 2 is 8 total results. And you can list them out. One way is heads, heads, heads. And it's kind of polar opposite would be tails, tails, tails. You could also go heads, heads, tails. Polar opposite would be tails, tails, heads. You could have heads, tails, heads. Or tails, heads, tails. Or you could have tails, heads, heads. Or what did I forget here? Heads, tails, tails. And there they are. That's what you could have with flipping a coin 3 times. There's one way to have all 3 heads. There's also one way to have absolutely no heads. So both of the NCAT probabilities are 1 in 8. And then 2 heads or 1 head are both 3 out of 8. There you go. So you can see what's happening is, and this should sit well with your intuition, it's getting harder and harder to get all of one result versus a mix of the results. As a matter of fact, looking at this, you're 3 times as likely to get a mix of heads and tails as you are to get exclusively heads and tails. So hopefully that makes sense. I don't want to keep drilling over this one, so we'll look at the 4 coin case in your homework. But I just want you to know you already looked at one of these in one of the early, I think it was a homework in the course, when we actually talked about what happens if you flip a coin 10 times, because that was one of the experiments I led the class with. And so you had already looked. I was kind of bleeding that distribution at you very early in the course. But again, a probability distribution has certain characteristics. First, it's got to list all possible values of a random variable. And that random variable should very well be numerical for what we're going to be doing with. And then it's got all the probabilities associated with each value next to it. And if you've done them correctly, these puppy dogs should add up to 100 or 1, 100% or 1. Okay? So that's looking at theoretical, coins, dice, things like that. But I think that's a nice place to start. So, of course, for the next day, we'll get into infinite theoretical distributions, which sounds terrifying, but it shouldn't be. And we'll also start looking at ones that you can only get empirically. But this is enough, I think, for day one.